right, let's dive in. Today, we're going deep on something called the renormalization group.
Ooh, sounds complicated.
Yeah, it can be.
Yeah.
But we're going to break it down, make it understandable.
Sounds good. And what are we looking at today to help us understand all this?
We've got some visuals and some text excerpts to guide us. So basically, what we want to figure out is how this theory helps us get a better grasp on the universe. Like how things work differently depending on the scale, like atoms versus galaxies, right?
All right.
And how we can actually connect the physics at those different levels.
It's amazing how renormalization lets us deal with all that complexity, picking out the important details at different scales.
Right, like zooming in and out. So I've got this image here. Just a glass of water.
Ah, simple, right.
You'd think, but think of all the physics happening in there.
Oh, absolutely. I mean, on a big scale, you've got classical physics, right? Like how the water flows.
Right, simple stuff.
But then you zoom in, like way in, you hit the atomic level, you're in nuclear physics territory. And even further in, you've got all these particles and forces.
My brain hurts already. But it's so fascinating. Okay, so different rules for different scales. Got it.
Mm-hmm.
But how do we connect it all? Is there like a theory of everything that ties it together?
Well, that's where our friend, the renormalization group, comes in. Maybe not a theory of everything, but it's like a framework, you know? Helps us understand how the physics changes as we change our perspective, change the scale.
So as we zoom out, we're not just losing information.
Not losing, more like shifting focus. It's called decoupling of scales. The bigger picture becomes independent of the tiny details.
So to understand how, let's say, water flows through a pipe, I don't need to know about quarks and stuff.
You got it. Don't need a PhD in particle physics for that.
Phew.
Renormalization helps us focus on what matters at each scale, like having different tools for different jobs.
I can dig that. Okay, now this next image talks about navigating a space of theories using the renormalization group. What's that all about? Sounds kind of trippy.
Yeah, it does. Think of it like a map. Every point on the map represents a different theory about how physics works.
Okay, I can picture that.
And the renormalization group is like a set of paths, showing us how those theories connect as we change scales.
So the numbers might change as we zoom in and out, but the underlying physics stays consistent.
Exactly. Imagine looking at a tree up close. You see all the leaves and branches. Step back, those details blur, but you see the overall shape of the tree.
Ah, okay, making sense. This is cool. But now these next images are making my head spin a little.
Yeah, the math can look scary, but it's the idea behind it that's important. It's about building something called an effective Lagrangian. Basically, a mathematical shortcut to capture the important physics at a specific scale.
So, like, for describing a gas, I wouldn't need to track every single atom.
Nope. The effective Lagrangian takes care of that. It gives you the overall behavior without getting lost in the details.
Awesome. But some of these terms are confusing. Like quasi-local.
Ah, good question. That just means interactions mostly depend on what's happening nearby. Think of gravity, stronger when you're closer, right?
Right. Makes sense.
And the other jargon you saw, differential polynomial of order. That's just a fancy way to describe the type of math we use. Don't sweat the details too much.
Okay, phew. So we're basically building a system for understanding how these effective Lagrangians change as we zoom in and out.
Exactly. It's like having a set of adjustable lenses to view the universe at different levels of detail.
I like that analogy. So are we losing information about the smaller scales with these Lagrangians?
Not losing it, more like encoding it differently. It captures what's important from the small scale for understanding the big picture. Think about compressing a file. Smaller size, but the essential data is still there.
Uh-huh. That's a good way to think about it. So we simplify, but keep the accuracy.
Exactly.
This is really changing how I think about everything being connected.
That's what we're going for. It's not just separate pieces. It's all one interconnected system with different layers of complexity. It's really amazing how interconnected everything is when you start thinking about it this way.
Totally. So we've been talking about how this framework helps us see the transitions between scales. But these next images focus on fixed points. What are those all about?
All right, remember that map analogy for the space of theories?
Yeah, each point is a different theory.
Right. Well, fixed points are like special landmarks on that map. Points where the theory stops changing even as we change scales.
So like a zoom on a fractal, the same pattern just keeps repeating.
Perfect analogy. And these fixed points are super important. They usually line up with those big changes in physics, like phase transitions.
You mean like water turning to steam?
Exactly. Or a magnet losing its magnetism when it gets too hot. Those are phase transitions, and the point where it happens, that's a critical point.
Okay, so by studying these fixed points, we can understand what happens near those critical points.
You got it. It's like a roadmap showing us not only the different states, but how to get between them. One famous example is the Ising model.
Oh yeah, I've heard of that. It's like a grid of tiny magnets, right? They can flip up or down.
That's the one. And it shows this cool phase transition where the magnetism just vanishes at a certain temperature.
So not just theoretical. This has real-world applications for understanding materials and stuff.
Absolutely. Magnets are just one example. Renormalization group is used for all sorts of stuff. Superconductivity, polymers, you name it. It's a real workhorse for understanding complex systems.
It's mind-blowing how this idea from quantum field theory is so useful in all these other areas of physics.
It's a testament to how powerful a good framework can be. It goes beyond its original purpose, connects different fields. And that's what's exciting about the renormalization group. It's like a bridge between scales, between different areas of physics, even between different ways of thinking.
I'm starting to see why this is considered such a big deal in physics. It's not just the math, it's a whole new way of looking at things.
Exactly. And as we dig deeper, you'll see how this new perspective can lead to some really incredible insights.
Okay, I'm ready for more. But these next images are taking us into some pretty sci-fi territory. They introduce something called dimensional regularization.
Ooh, yeah, that's a fun one.
It's about dealing with infinities that show up in quantum field theory calculations. Infinities! That doesn't sound good.
It's one of the tricky things about working with quantum field theory. You try to calculate something and boom, infinity. Seems like the math is broken.
Yikes. So how do we fix that?
Don't worry. Dimensional regularization is like a mathematical trick, a clever way to tame those infinities so we can actually get meaningful results.
The images talk about doing calculations in a space with a non-integer dimension. What does that even mean? Like, are we stepping into a parallel universe with 4.2 dimensions?
It's a wild idea, right? Think of it as temporarily leaving our 3D world and going into a space with, let's say, 4.1 dimensions or 3.8. Sounds strange, but it's a powerful tool.
Okay, I'm trying to wrap my head around it. But how does this help with the infinities?
The trick is that in these weird fractional dimensions, the infinities become easier to handle. It's like spreading the problem out, giving it more room. And then we use something called analytic continuation to bring our answers back to our normal 3D world.
Analytic continuation. That sounds intense.
Think of it like having a map of a small part of a continent. Analytic continuation is like extrapolating, using that small map to figure out the whole continent, even the parts you haven't seen.
Okay, so we're basically using this higher dimensional space as a workaround to deal with the roadblocks in our calculations.
That's a great way to put it. It's like taking a detour through a different dimension to avoid a traffic jam. Then, once we're past it, we use analytic continuation to get back on the right path.
So we're not actually living in a fractional dimension, just using it as a tool.
Exactly. Dimensional regularization is a technique, not a description of reality. It's like a mathematical trick to help us make sense of the physics.
It's blowing my mind. If we can use these abstract tools to handle infinities in quantum field theory, what other impossible problems can we solve?
It's amazing what we can do with math and human ingenuity. Who knows what other breakthroughs are waiting for us? This is just the beginning.
This is incredible. We started with a simple glass of water, and now we're talking about dimensions and infinities. And the amazing part is it's all connected.
Right. That's the power of the renormalization group. It helps us see the connections, the big picture, how the universe is interconnected at all these different scales.
I feel like I have a whole new understanding of how the world works, but also realize there's so much more to learn.
That's the beauty of science, right? It's a journey of constant discovery.
For sure. But before we get ahead of ourselves, we've got one more part to this deep dive. We'll be right back after a short word.
All right, we're back. This deep dive into the renormalization group has been a wild ride.
Definitely covered a lot of ground. But I want to touch on one more thing before we wrap up. We talked about how this framework could apply beyond physics, right? Even help us solve problems in our own lives.
Yeah, that really piqued my interest. Well, think about decoupling of scales. How some details become less important when you look at the big picture. That's relevant to any complex situation, not just physics.
So like how physicists analyze the universe could help us with a tough work project or making a big decision.
Exactly. We often get lost in the tiny details of a problem and forget about the big picture. What if we did a sort of mental renormalization? Focus on what really matters, the key factors.
Like mental decluttering. Figure out what's essential and ignore the rest.
Right. Not all information is equally important. Like, you don't need to know about every atom to understand how water flows.
Makes sense. So we simplify without losing sight of the goal. Are there any other principles from the renormalization group that we could use in real life?
Well, what about those fixed points, those stable points in the space of theories? Think of them like our goals.
Okay, I'm following.
By focusing on those fixed points, our goals, we can navigate through all the complexity of life, make choices that move us toward those outcomes.
Like having a compass to keep us on track, even when things get crazy.
That's it. And just like the renormalization group connects different scales in physics, it can help us connect our everyday actions to our long-term goals.
This is so cool. Who knew theoretical physics could be so practical?
It's amazing how science can do that. Helps us understand the universe, but also ourselves.
This deep dive has been mind-blowing. From atoms to galaxies, uncovering hidden connections, and changing how we view reality.
And we learned that the principles governing the universe can also guide our own lives, helping us handle complexity, make smarter choices, and see how everything's connected.
This is just the beginning of our exploration. Keep those minds curious, and join us next time for another deep dive into the amazing world of science.